Okay, so a very good evening, sir. This is Group 11, and the objective of this experiment is to reduce the amplitude of vibrations of a beam with an unbalanced rotor using a tune mass. So, give you a basic overview. So, basically, a tune mass damper serves as a really good tool for controlling the vibration, and it comprises of a spring mass and a damper. So basically, in this experiment, we will see how it's effective in mitigating the vibrations in a cantilever beam and experiencing the harmonic excitation from an unbalanced rotor. We will also study and study basically aims to explore the fundamental resources phenomena seeking to dampen the resonant vibrations through precise TMD parameter adjustment. So TMDs find widespread applications across industries like from damping rotational motion in ships to enhancing the structural stability during seismic events and reducing vibrations induced by the aerodynamic forces in an aerospace application. So regarding the fabrication details, so the stand that we used was created with a MDF sheet, 4 millimeter thick MDF sheet, which we cut it using the laser cutting machine. I will show you the setup of our experiment. So this is our setup. As you can see, this is the scale, 30 centimeter scale, which will we use as a cantilever beam. And at the end here, you can see it's a 5-volt rotating motor, which will create a resonance across the cantilever beam. And this is a spring that will basically mitigate the like vibrations. And at the end here is a mass that will help control it. Next, moving on to the uh, yes, the mathematical modeling. Let me get over to the switch.
Uh, Hello, yeah. So let us look at the mathematical modeling for the cantilever beam. As can be seen in the figure, the cantilever we are using is fixed at one end and free to move at the other. So for free vibrations of a bending beam, the governing equation is a partial differential equation of the fourth order, which is represented in equation one here, where E is the elastic modulus of the material, R is the area moment of inertia for the beam, and rho is the linear mass density of the beam. To solve this particular fourth order partial differential equation, we have used the variable separation method, and where we have assumed that the v of x of t is independent functions of x and t. So writing that in substituting that in equation one, we get equation two. Now, if we look at equation two, we can see that the left-hand side is independent of time and completely depends on the position, whereas the right-hand side depends on time and is independent of the position of the beam. So using this, we can come to a conclusion that both these values should be equal to a constant, and that particular constant is equal to omega n square, which is the natural frequency of the beam. So rewriting these two differential equations and solving, we get x as can be seen in equation number 3. To solve for the constants, we use certain boundary conditions, whereas which are shown in 3a, 3b, 3c, and 3d, where fixed end must have zero displacement, the fixed end must have zero slope, fixed end as in x equal to 0, and at the free end, which is x equal to L, the bending moment is 0 and the shearing force is 0. Using these equations, we we come to the final answer. Yeah, we get these. So this can be done only when CT and C2 and C4 are 0. And finally, solving all these, we get the following equations, which is cos of Kn of x into cos h of Kn of x is equal to -1. And solving these, we can get values of Kn and omega n. For n equal to 1, we get omega 1 as pi square by 4 into 1 by L square into under root of EI by rho A.
Uh, Moving on to our experiment. Let me just open it. Next, we have a source of mismatches and source of improvement. So, what are the sources of mismatches and source of improvement?
Yeah, so the choice of TMD might not be optimal for the specific characteristics of the beam and rotor systems, leading to suboptimal vibration reductions. The location of TMD on the beam might not effectively target the areas experiencing the highest vibration amplitude, reducing its efficiency in vibration suppressions. And the experiment might overlook external factors such as damping in the system, which could affect the resonance behavior and the effectiveness of TMD. Scope for improvement are like conducting a detailed analysis of beam rotor system dynamics, including model analysis and frequency response studies to better understand the resonance behavior. Then we can implement a systematic approach to select the most suitable TMD parameters like mass, stiffness, damping, based on the specific characteristics of the beam rotor systems and desired vibrations, reduction targets. Then we can utilize advanced modeling techniques or experimental model analysis to identify the optimal locations for TMD placement, incorporating damping effects and other external factors into experimental setup to better simulate real world scenarios. And the last is conducting rigorous experimental testings with multiple configurations and scenarios to validate the effectiveness of proposed improvements and ensure reliable results.
Thank you, Smith, and thank you very much, sir.